Having defined the graph Laplacian matrix, now let's start thinking about how can we use the graph Laplacian to find a good partition of our graph, right? So basically, we want to go back to our original problem where we want to find how to split the graph into two pieces such that the number of edges kind of crossing the two pieces is small. The way we will do this is by basically thinking about what do eigenvalues and eigenvectors of this graph Laplacian matrix, what is their meaning. So the important fact that we'll be using, and I will just state this fact without proving it, is that yeah, if I think about what is the value of the second smallest eigenvalue, then one can show that the second smallest eigenvalue is simply a solution to the following problem. So let's think of M as being some matrix, X is some vector over which we want to solve things, and basically lambda 2 is a solution to the problem that we want to minimize, x transpose times M times X divided by X transpose times X. So basically, lambda 2 is a solution to this equation. So now let's start asking about what is the meaning, for example, of, in our case, of the graph Laplacian. So what is the meaning of X transpose L times X, right? So now L kind of plays the role of our matrix M above. So what is the meaning of this expression, right? Where I take a vector of entries X, multiply it with L, and then multiply the whole thing again with X from the left side. So let's write this out. What does it mean to multiply X transpose times L times X, right? So this is simply a summation over I and j, right? So it's a double summation where I take Lij, Xi, Xj. Now, instead of writing Lij, let's write out what is the definition of L. So the definition of L is simply the degree matrix minus the adjacency matrix, right? So instead of writing Lij, we will write Dij minus Aij. So what we will do now is we will go and distribute Xij inside the parentheses. So what we will get is, for the first part, we will get a summation over I dii xi squared, right? The reason we get this is because D is a diagonal matrix. And then for the second part, all we have to do, right, we remember what is A times X, and A times X is simply the sum of the values of the neighbors. So basically, this is simply a summation over all the edges of our matrix. And now, because I have Xij, I see it twice, so I have to do twice Xi times Xj. So this is now how we can rewrite the whole product from the beginning. But let's start thinking more about it. Actually, what we can do now is we can take this product and do one simple thing. Let's add X. What we notice is that the sum over the degrees, right, dii times xi squared, the way to think about this is basically for every node we have to take its squared value entry and then sum it up together d times. What this basically means is that we can take the squared value and sum it up once for every edge, right? And this is exactly what we did here, right? Instead of taking degree of node I times xi squared, we now pushed this squared value of node I into the summation over all the edges, where what we notice here is that because a given node has degree d, this means that for that given node I, we will sum xi squared d times. So the whole thing is equivalent. Now, of course, each edge has two endpoints, one on one side, one on the other side. So we also have to have xj squared. And what we notice now, that this is simply a summation ij over all the edges, where I have xi squared plus xj squared minus 2 xi xj, right? This is from before. So what do we notice now is that this is simply a summation over all the edges, xi minus xj squared, right? So what we have just shown is that x transposed Lx equals to a summation over all the edges, where I take the label of one endpoint of an edge, subtract the value of the other endpoint of an edge, square it up, and sum this over all the edges. So now let's start thinking about what is really the meaning of this expression. If we now go and actually think about what do we know about x, right? There are few things where x is now the solution to the lambda 2 eigenvalue problem, right? So there are few things we know about x. The first thing we know about x, because x is an eigenvector, we know that x is unit length, right? It basically means we know that the sum of the squares of the entries of x equals 1. So that's the first thing. The second thing we also know is that x is orthogonal to the first eigenvector, right? We have already convinced ourselves that eigenvector of, or a vector of values 1 is already the eigenvector of our Laplacian matrix L, and that the corresponding eigenvalue has value 0. So now, given that x is orthogonal to this vector of all ones, basically what this means is that when I do a dot product of x with a vector of all ones, I should get 0. What this basically means is that the sum of the entries of our x should sum up to 0. So now we have two things. First is that sum of the squares of entries of our vector x should equal 1, and sum of the entries of x should equal to 0. Okay? So now let's go back to our original problem of what is the value of lambda 2 and what is the corresponding eigenvector x. We said that this is x transpose times L times x. Now we convinced ourselves that the first part is simply a summation over all the edges label of node I minus label of node j squared. And at the bottom, we are dividing by x transpose times x, which is simply sum of the squares of the entries of vector x. We already know that sum of the squares of the entries should be equal to 1, so this is 1. And basically all that is left here is this summation over all the edges, where I take the differences of the edge endpoints, right? So now the way we can think about this minimization problem is simply we are going and minimizing over all the labelings of nodes I, such that the sum of the labels of all the nodes equals to 0. And what we are trying to do is we are trying to do these labelings in such a way that the sum of the squares of the labels equals to 1. And we want to minimize the value of discrepancies between the labels of edge endpoints, right? So in some sense, what this means is we have to think about this the following, right? Basically, what we are trying to do is we are trying to take the nodes of our graph G, right? So here's our graph G. We want to put some of the nodes to the left-hand side of 0, and we want to put some nodes to the right-hand side of 0, right? If here I think of this as a real valued axis, right? And now what we would like to do is the following. We would like to, the reason why we have to put some nodes to the left of the 0 and some nodes to the right of the 0 is because we need the sum of the components of x to be equal to 1. So we have to have that. The reason why we cannot put all the nodes on one side or all the nodes on the other side is because we want the sum of the individual components of x to be equal to 0. This means that for every kind of node that we put on the positive side of the real line, we have to put something on the negative side so that the whole thing cancels out. And now let's also think about what is our minimization problem. Our minimization problem basically says that we want to minimize the sum of the differences of labels across all the edges. This basically means that what we would like to do is we would either like to have for all the edges both nodes to be on the left-hand side, because then I have a negative number minus a negative number, so the difference will be small. Or I would like to do this for nodes that are connected and are on the right-hand side of 0. Again, that the labels cancel out so that there is a positive label minus a positive label. And if we think when we will really be penalized here in the sum of the differences is when we have an edge that crosses 0. Right? In that case, we'll have a positive label and we'll have a negative label. So they will basically sum up together. Right? So what this is basically saying is that this minimization problem, what it's trying to do, it's trying to put nodes on a graph. It's trying to kind of put them on a real line in such a way that the number of edges that span across 0 is as small as possible, while the nodes that are connected with each other, they are basically on the same side of the real line. And this is kind of exactly what we want to do, right? We want to minimize the number of edges crossing, while we want to put some nodes on the left-hand side and some nodes on the right-hand side. So basically, what is the point? The point is that the eigenvector that corresponds to the second smallest eigenvalue of our graph Laplacian L is basically doing the right thing, right? It's basically trying to assign labels to the nodes such that some nodes have a positive label, some nodes have a negative label, and the sum of the discrepancies of the node labels across all the edges is as small as possible. So basically what we have learned is we can go basically back to our original optimization problem, and we can express how to find the optimal cut in the following way. Let's think of yi to be a binary vector where +1 means that node I corresponds to the left side of the partition, and -1 means that our node I corresponds to the right-hand side of the partition, right? We can think of a set A and a set B, right? And the idea is that we can minimize the cut of the partition by finding the non-trivial vector x that minimizes the following condition, right? So basically, the equation is I want to assign labels +1 and -1 to all the nodes in the network in such a way that the sum over the edges of this network, yi minus yj squared, is as small as possible, right? So basically what this is saying is I want to embed nodes of my graph onto the real line, where some nodes can have only coordinate -1, other nodes can only have coordinate +1, and what I would like to do is, if the nodes are connected and they are both on the same side, I will have, let's say, -1 minus -1 is 0, so I will get no penalty. And basically the only time I will get a penalty here will be when one for an edge where one of the nodes is on the left-hand side and one of the nodes is on the right-hand side, right? So what does this mean? This means that the way we find a bisection is to put some nodes on the left, some nodes on the right, in such a way that the number of edges crossing the two sides is as small as possible. So this was kind of first observed and noted down by Fiedler in 1973. So now, basically, what we are learning is that we can go and relax our problem a bit, right? So instead of thinking that we can only put nodes on left and right and assign them labels -1 and 1, let's now allow to assign them values that are real valued. So what this basically means is that our original minimization problem, which was this f of y, and we said, let's go and minimize the sum of the discrepancies of labels of nodes at the edge endpoints. This is simply us saying this is y transposed our Laplacian matrix L times y. So basically what this means is that, as I mentioned before, we are trying to assign nodes to the left and to the right-hand side of 0 in such a way that the sum of the labels equals to 0, sum of the squares of the labels equals to 1. And we want to also minimize the sum of the differences across the edges, which basically means we want to have lots of edges to be between the nodes on the same side of 0 and a few edges that kind of cross between the two sets. So we already know what is the solution to this kind of minimization problem. We know that lambda 2 is the solution or the value at which this minimization is solved. And we already know that the vector that solves this minimization problem is the second smallest eigenvector. And this vector is called the Fiedler vector, or goes under the name of a Fiedler vector. So what this basically means is that the components or the labels of nodes that come from the second smallest eigenvector, they will tell us which nodes to put in one cluster and which nodes to put in the other cluster.